Question 2. So the last question we looked at you colliding with a street lamp. Quite unfortunate. However, thankfully, you and your car were unscathed during the collision. Roadside services checked your car and you moved on with your road trip. So you went to the nearest arcade to de-stress, as you do. So part A, you played pool. And if you know, in pool, or billiard balls sometimes called, you have a cue stick and you hit the pool balls into each other to go into the holes. So you hit the stationary white ball with a speed of 5 meters per second. So here's your cue stick. You hit it to the left. So here's the ball. So your cue stick is moving to the left. The ball is stationary, right? And so you pull back and pop, you hit the ball. And then what happens? Well, the white ball would start moving, right? Now, the stick has a mass, the ball has a mass, and assume that the stick comes to rest after the collision. Right, so you hit it, like pop, and then it stays put. While the ball would then move forward to hit other balls. So that's the scenario. Part 1, state the condition required for the conservation of momentum. So for momentum to be conserved, it must be an isolated, or another word is closed, system. And what that means, no external forces. Things like friction would get in the way of momentum being conserved. So once more, in order to have a system where momentum is conserved, it must be isolated. In other words, there are no external forces. Part 2, calculate the initial momentum of the system. So initially, the ball, which has a mass of 200 grams, so let's write that in kgs straight off the bat, is stationary, so it has no momentum. However, the cue stick, which is moving at 5 meters per second to the left with a mass of 0.5 kgs, will have a momentum, right? So the initial momentum of the whole thing would just come from the cue stick. But let's write it out in full. So I'll bring this down here. So the initial momentum is the initial momentum of the ball, so I'll use B, plus the initial momentum of the stick, so I'll use S. The initial momentum of the ball is the mass of the ball times the initial speed of the ball. Similarly for the cue stick, its initial momentum is the mass of the cue stick times its initial speed. Now looking at the mass of the ball, that was 0.2. However, its initial speed was 0. Plus the mass of the cue stick, 0.5 kgs, times its initial speed of 5. And you'll see that the momentum of the ball is initially 0. And so we're left with the initial momentum as 2.5 kilograms meters per second. And that comes from the cue stick, right? 0.5 kgs times 5 meters per second. That is the initial momentum of the ball and stick system. Part 3, calculate the final momentum of the system. Well, if this is an isolated system, which we will assume it is, so let's say assuming isolated system, the final momentum will equal the initial momentum, which is 2.5 kilograms meters per second. Right, so the final momentum of the system, PF, that looks like PP, it's PF, head out of the gutters please, thank you. PF, final momentum, 2.5 kilogram meters per second, which is the same as the initial momentum because momentum is conserved in an isolated system. Cool. And writing this, PF equals PI, shows your understanding of that. That's all we need to write. Part 4, calculate the change in momentum. Now this question should be change in momentum of the ball. Let me just fix that. So what would its change in momentum be? Now this time we're looking just at the ball, not the whole system. So part 4, for the ball only, what is the ball's initial momentum? Well, it was 0, right? Because it was stationary. So let's write that. PI is 0 as it was stationary. Now what is the ball's final momentum? Well, we know that the final momentum of the system, so of the ball and the cue stick, is 2.5 kilogram meters per second. After the collision, it says the cue stick comes to rest. So what would the final momentum of the cue stick be if it comes to rest? So that would also actually be 0. However, we know that the whole system must have 2.5 kilogram meters per second of momentum. So that would all go into the momentum of the ball. So the final momentum of the ball is 2.5 kilogram meters per second. So back to the question, calculate the change in momentum. Well, it goes from 0 and it gains 2.5 kilogram meters per second to the left, right? Because it is now moving to the left, so its velocity is to the left. So change in momentum, delta P, is PF minus PI, 2.5 minus 0 to give 2.5, and we will say to the left. Right, momentum and change in momentum is a vector, so magnitude with direction. And so what would the change in momentum of the cue stick be? So it's moving initially with 2.5 kilogram meters per second to the left. If it comes to a complete stop, its change in momentum would actually be 2.5 kilogram meters per second to the right. Okay, and part 5, if the collision with the cue stick and the ball lasted 1/10 of a second, calculate the force experienced by the ball, including the direction. Well, starting with the direction, we know that the force acting on it would be to the left, right, in order for it to accelerate to the left, to move to the left. But let's work out the magnitude as well. Looking at our formula sheet, we know impulse, or change in momentum, is the collision force times the time of collision. So rearranging for force, change in momentum over change in time, where the change in momentum of the ball was 2.5 and the time was 0.1 seconds. So that's 2.5 divided by 1/10, which is 2.5 times 10, so that's 25. and units for force are newtons. And the direction, as we said, is to the left. So the ball experiences 25 newtons of force from the cue stick to the left. And that's part A all done. Part B. Now, the white ball has a velocity of 5 meters per second, perpendicular to the wall. It then collides with the wall. The collision lasted 0.2 seconds. So if it was traveling 5 meters per second before, and it rebounded with 4 meters per second after the collision, explain why the final speed is less than the initial speed. So why did it not bounce back with 5 meters per second of velocity? So let's just draw a diagram to help understand the problem. We have the side wall, the white ball moving at 5 meters per second, perpendicular, right, so at 90 degrees. It hits the wall. After its collision, the ball, or the egg, the ball has bounced back off of the wall at the same angle, 90 degrees, but with a lower velocity. So where did that speed go? So let's start with what types of energies are involved, right? Energy is always a great concept to fall back on to explain pretty much anything in physics. So let's try use it here. So initially, the ball has kinetic energy, and we could actually work that out, right? Because that's just half times its mass times the speed squared. But we're just explaining, so we don't actually need to show this calculation, but you could. After the collision, or after, the ball has less kinetic energy as V has decreased. So see how we went from 5 meters per second down to 4. So speed has decreased. So the ball now has less kinetic energy. But we know energy can't be created or destroyed. So where did it go? This difference in energy went into a few things. Most of it would have gone into the wall as elastic potential energy. As it deformed. Right, so in order to deform something, to make its shape different, such as a wall, you need to push into it, and that energy goes into changing the shape of the wall slightly. So some energy is lost to elastic potential energy. Other losses could be into heat and sound, right, due to friction. And that will explain why the final velocity is less, because it has less kinetic energy, as the energy was transferred to less useful things, such as potential energy of the wall and heat and sound due to friction. Part 2, calculate the force imparted onto the wall by the ball. Okay, so we're looking for a force. We're given information about the collision time, its initial speed, and final speed. So, similar to question A, when we looked at part 5, we need to work out the change in momentum of the ball. to work out the force on the ball, but then get the opposite direction to find the force on the wall. That's a lot of alls. Let's just do it. So let's say for the ball, its initial momentum is, so it has a mass of 0.2 kgs and an initial speed of 5. 0.2 kgs mass times velocity 5, which is 1 kilogram meters per second. Its final momentum, same mass, but only a speed of 4 meters per second. However, we need to be careful with our signs here. So let's define, according to my diagram, to the wall is positive, so away from the wall is negative. So back to our initial momentum. Its initial velocity is towards the wall, so it's positive. That's fine. However, our final momentum needs to be negative. Our final velocity is negative because it's away from the wall, which will also make our final momentum negative. Okay, so let's have a think. So initial momentum positive towards the wall, final momentum negative away from the wall. Now to find the force, we know we're going to need the impulse, which is the change in momentum. So final minus initial, final negative 0.8 minus initial 1 to give negative 1.8. And notice if that was a plus, our change in momentum would actually be 0.2, which doesn't really make sense, right? Because that would be positive, so that would indicate the ball's like moving through the wall. So it pays to just pause, think about the signs for a moment. So we have our change in momentum. We can link that to the collision force by change in momentum over change in time. So negative 1.8 divided by the time, which was 0.2 seconds. Which is exactly 9 units for force are newtons. Oh, negative 9 newtons. And so what does this number tell us? So this is the force acting on the ball for it to change momentum and go the opposite direction. Right, so negative means the force is acting down. So as the ball hits the wall, it experiences a force acting down, exactly 9 newtons, to push it with a velocity of 4 meters per second the other way. But the question asked, what was the force on the wall? So that would actually be equal but opposite in direction to that 9 newtons. So our final answer, so F against the wall is 9 newtons, and we could say into the wall, right? Or how I've drawn my diagram, I would say up. But if you drew your diagram on its side, you could say right, as long as it's into the wall. Part 3, how could you change the ball or the wall so that its final speed is closer to its initial speed? So going back to part 1 here, some of the energy was lost into potential energy of the wall or heat and sound due to friction. So we would like to reduce that. A few ways we could do that. So we could say, what should we start? Friction's easiest to start with. We could reduce friction on the ball and the wall so that less energy is lost. I'll use like quotes there because it's not lost, right? Let's use our proper words. Less energy is transferred to heat or sound, leaving more energy for kinetic, right? In other words, it's speed. And in fact, if we had all of the energy remaining as kinetic energy, its final speed would be the same as its initial speed. So we want to reduce the friction so that less energy is transferred to heat and sound, leaving more for kinetic energy. So that was the friction component, but we also mentioned about the potential energy of the wall as it deformed. So if the wall was like very, very stiff, it had no give to it, it wouldn't be able to deform as much. So that's another thing we could change. So the wall could be stiffer, not deforming as much, allowing, or again, leaving more energy for kinetic energy or its speed. So either of those two things will result in a greater final speed. Alright, part C, last one. Now the white ball collides with the stationary 8 ball, also 200 grams. The collision lasts 0.12 seconds. The black ball experiences a force. And if the white ball was traveling at 5 meters per second before and 0.5 meters per second in the opposite direction after, calculate the velocity of the black ball. Alright. So I see a mass, I see a collision time, I even see a force now. We have an initial and a final speed for the white ball. If the black ball or the 8 ball is stationary, that tells us its initial speed is 0. And we're looking for the final velocity of the black ball. So this is definitely a change in momentum problem, right? But the catch here is we're given force, which we can relate to change in momentum through the impulse equation. So let's get to it. Question C. The force was 10 newtons. The time of collision was 0.12 seconds. I think, yep. The white ball was, 5 meters per second and then negative 0.5. Just listing out everything we know. What else do we know? We know the mass of both are 0.2 kgs. for the 8 ball, its initial speed was 0, final speed is what we're looking for, and its mass was also 0.2 kgs. I think that's everything. And notice I already incorporated a negative sign. So I'm taking, let's just go positive to the right, and so negative will be to the left. And so the white ball is moving 5 meters per second to the right. It hits the black ball and it bounces back with 0.5 meters per second. So since it's going backwards, I put the negative sign. Alright, where to begin? Well, rather where to end, right? The final velocity of the black ball. So to get velocity, if we know the final momentum of the black ball, we could work it out. So how do we get momentum? Well, we could first work out the change in momentum of the system. So change in momentum is the collision force times the collision time, which is 1.2 kilogram meters per second. And does that sign make sense? So let's go back up to the question. What was the force telling us? The black ball experiences a force of 10 newtons. Yeah. So since the white ball is going to collide with the 8 ball, the 8 ball will experience a force to the right during the collision. So the force should be positive, which it is. So what is this change in momentum of? Well, that's of the 8 ball. And it's also of the white ball. What next? So we can work out so now we can look at the 8 ball. In fact, we can actually ignore the white ball, because we're looking for the final speed of the 8 ball. So if change in momentum is final minus initial momentum, and we know that that must equal 1.2, positive 1.2, because it's going to the right, we can write the initial momentum of the black ball, mass times initial speed, 0.2 times 0, which gives 0. The final momentum is mass times final speed, which is what we're looking for, so that's 0.2 VF. Now we can put these three equations together. So where change in momentum, 1.2, is final momentum, 0.2 VF, minus initial momentum of 0, and solving for VF, well, minusing 0, that's quite easy, right, minus nothing. So we can then divide both sides by 0.2. So VF is 1.2 divided by 0.2, which is 6. Let's double check. Yep. Meters per second. There we go. So now does that sign make sense? So it's positive. Yep, according to our diagram, after the collision, the white ball moves back a little bit, and then the 8 ball should be moving to the right in the positive direction. Cool. So just to recap this last question, we were given information about the white ball, which was actually what's called a red herring, like great to know, but kind of useless in helping us answer the question. Because we knew the force of the collision and the time, which let us work out the change in momentum of the 8 ball. Then using that and its initial and final momentum, we could solve for final speed. Alright, I think it's about time I go to the arcade and play some pool. Enough physics for today. Make sure you take a break, and happy studying.